Oxidation, which is chapter 3. Okay. Well, oxidation, we are particularly going to discuss about the silicon oxide, which is this is the thermal, we call the thermal oxide. Okay. And this happens at the elevated temperature, like I think it has to be more than 900 degrees centigrade, and typically is done at 1000 degrees centigrade and 1100 degrees centigrade in between. Okay, so in the note, it has a summary of the characteristic of silicon oxide. Okay, this silicon oxide is amazing material. This is basically amorphous, and we can crystallize this thing, and if it is crystallized, it is going to be called quartz. Expensive material. Okay. Well, there are many beautiful characteristics of silicon oxide, and that has been summarized in the note. But I want to emphasize two things among those characteristics. One is the excellent dielectric properties it has. Okay. And the other thing is the volume change. After oxidation. Well, firstly, about the excellent dielectric properties, let me give you the example of three different kinds of oxide. The first, the common thing is the iron oxide, Fe2O3. We can have oxidation continuously so that we can have a thick oxide, okay? But it is not dense enough. We just scrub off. We can scrub off the oxide, iron oxide, okay? So it is not dense, but it has a continuous oxidation. It's possible. Continuous oxidation is possible. Another form is the aluminum oxide. Is very dense. This oxide is very dense, and it has a passive layer, so that only 50 angstrom of oxide is formed, and then no more oxidation can happen. Oxidation cannot be continued after the 50 angstrom of aluminum oxide. So that's why this aluminum oxide can be used as a can for beverages. Okay, it's safe. You cannot use the iron steel for the beverages can. If you do that, then you are going to have iron oxide continuously, and that iron oxide can be scrubbed off from the surface after the oxidation. But silicon oxide is in between of these things so that it can be used in VLSI, semiconductor fabrication. It is not very dense, but dense enough to have a good dielectric properties. Okay, and then we can grow 1 or 2 micron of oxide. The oxidation rate is not that fast, but we can grow the silicon oxide on top of the silicon surface up to 1 to 2 microns. And that is thick enough to be used for the VLSI. So this is the gift from the God, we should say. Okay. If this silicon oxide is to have the properties of iron oxide, then it cannot be used for the semiconductor fabrication, transistor fabrication, whatever. And if it has an alumina characteristic, also we cannot use this silicon oxide for the transistor fabrication. So it's very fortunate to have that silicon oxide with that properties, and the more importantly, it is not that difficult to have a silicon oxide to form a silicon oxide on top of the silicon. All we have to do is just to put the silicon in the furnace in air at elevated temperature like 1000 degrees centigrade or 1100 degrees centigrade. That's all that we have to do. Okay, and the second characteristic of silicon oxide, which is volume change after oxidation, that is the beautiful thing, that turned out to be very important in the fabrication of a VLSI. Now, when you say the volume change, it means that if you have a silicon surface like this, and after the oxidation, you're going to form some oxide, and some goes down to the silicon surface, and some goes out to the silicon surface, so that this whole thing is the silicon oxide, and the distance from D1 is equal to D2, so that the volume is doubled, I should say. Okay? That is a volume change. And let me introduce local oxidation of silicon. We call this locus process. It's a very famous and very essential process for the VLSI. What we are doing here is that we have a silicon surface here, and then first we put the oxide. We grow thermal oxide. We call that base oxide. Base oxide, and this base oxide thickness is about let's say 300 angstrom or so, not that thick. Okay, and then we deposit the nitride on top of it, and this nitride, silicon nitride, the thickness of silicon nitride is about 1000 angstrom. Okay, and then we do the lithography to get a pattern and etch the silicon nitride and the silicon oxide, so that we are going to have an opening something like this, and then do the oxidation of this. this silicon nitride is going to block the reaction of the silicon with the oxygen, so that we end up with some shape, something like this. Okay. This is one end, and at the other end has the same shape like this. Because of the volume change, we have some lifting of this silicon nitride. Okay, and this is the silicon oxide, the silicon. So when this area is going to be oxidized, then it's going to change the volume, and at these edges it's going to be lifted due to the volume change, so that we end up with this thing. Why do you want to have this? Because, you know, integration means we are going to we're going to fabricate independent transistors and collect them in a certain area, electrically independent. Okay? So what we are doing here is that we are going to physically separate the transistors in the VLSI by this oxide, by formation of this oxide in between. Okay, so here, let's see, that is one transistor, and each transistor is going to be separated by we call that field oxide. This is going to be called the field oxide. Okay. That is the cross section of the integrated circuits. Now, when we integrate these transistors, we are going to separate these transistors electrically by formation of silicon oxide in between. Okay, so in the real process, what you do is, in the silicon surface, you form the silicon oxide first, the field oxide first. Okay, and then you make transistors on this area in between the field oxide, and this area is going to be called active area. Okay, active area, where the silicon transistor is going to be implemented. All right. So at the very beginning of a VLSI process, we have to form the field oxide to define the active area. Okay. And for the formation of field oxide, we take advantage of a volume change by the oxidation, and then we end up with this thing. And you see in the class note, this has been shown, this low-cost process here, and this is the actual cross-section, SEM cross-section of the field oxide. This is the field oxide, and this is the silicon nitride, okay? And then we call this bird's beak. Bird's beak. We call this, this thing is a bird's beak. Bird's beak. You know what the beak is? Bird's mouth. Okay? The shape just look like a bird's beak. So we call this bird's beak. And there are two other different ways to make a field oxide. Okay. Oh, another thing is. Oxide, we call this oxide isolation. And we have three methods. Number one is fully recessed. And number two is non-recessed. Number three is semi-recessed. So the bird's beak happens in this semi-recessed process. Semi-recessed means if it is a silicon surface, field oxide is going to be formed half on top and half on the bottom. Okay, so this part is just a half recessed, depressed. That's why it is called the semi-recessed. So fully recessed means if it is a silicon surface, then you etch the certain part of the silicon surface before the oxidation, just a half of the oxide thickness. And then do the oxidation, then you end up with silicon oxide. So that the surface is the same, is a planarized surface. This is the fully recessed oxide. But in actual process, it never happens like this. Okay. As we have a bird's beak here we are going to have a bird's head instead of a bird's beak. Bird's head. Because you have a nitride here, and then the nitride is going to be lifted at this edge, okay? And the shape has been shown in the note where this is the fully recessed locus, so that the surface here is almost the same, right? Here we have a nitride, and the nitride is going to be lifted up here like this, and then oxide is fully recessed, so that we have this shape. And we call this, it just look like a bird's head, so we call this bird's head, okay? That's a fully recessed. So this thing, a bird's head. And a non-recessed is just nothing but we have a silicon here, and we deposit the silicon oxide or form this thermosilicon oxide, and then some part is etched with a lithography, so that we have just like this. Okay. What is the drawback of this process? The drawback of this process is that obviously, if we have a silicon oxide, something like this, and then you form a gate and source, something like this, in between this non-recessed silicon oxide. Now this transistor and this transistor can communicate, not electrically isolated, because there is no silicon oxide underneath this silicon oxide. Okay, so it is not really blocking the communication between the transistors in a non-resistive process. But more importantly, it has a drawback we call the residue. Now, if we have just a stiff clip like this, okay, and then on the next process, if you deposit some film on top of this and then do the edge, then this part is going to be etched in this fashion, thicker than the other areas, so that after etching, you end up with this kind of shape. Okay, you have some residues along the side of this, along the wall, we should say, of the silicon oxide in the right angle. Okay, so in the real transistor, you are going to have something residues along the vertical direction of this whiteboard, right? And if this is a metal film, then it's going to shoot every transistors along these directions. So we do not want this residue. So why we call this semiconductor recess, the silicon oxide volume change is beautiful for the VLSI integration, is that when you do this, okay, we have a buzz beak, but we have a smooth curve here because of the volume change. That smooth curve is very important, preventing the residues and post-processes. Okay, so if you want to do that intentionally, that is not easy to have this smooth curve. That is called tapering. Okay, we sometimes artificially make that right angle smooth. We have some many means to do that, and we call that process the tapering. Okay, it's complicated, but in case of silicon oxide and in the semi-resistor processes, naturally the smooth curve can be formed after the oxidation, and so it is so beautiful. Now, the drawback of this semi-resistor process is that this bird's beak, literally from here to here, where we have a slope, in between, that is this area is going to be called the bird's beak. The oxide, the silicon oxide in this region is too thin for field oxide and too thick for gate oxide. Okay, so it's just a waste. Bird's beak is waste. Okay, so when you do the integration, the silicon surface, every piece of silicon surface is very precious, very important. That is the place where the tiny transistors is going to be built, right? But this bird's beak area is just a waste because it is no good for the field oxide and no good for the gate oxide. We can do nothing at this Bursvik area. So that is, many research has been focused on reduction of this Bursvik length. How we can decrease the Bursvik length? Well, that is related to this, okay, base oxide, the thickness, and the nitride, the thickness. If you have a very thin base oxide, less than 300 angstrom, for example, then the Bursvik, the side diffusion of the oxygen underneath this mask is going to be prohibited. Okay, less diffusion can occur if this base oxide is very thin. Okay, so the Bursvik is going to be reduced. Bursvik length is going to be reduced. Or if you increase the thickness of the silicon nitride, then the silicon nitride is a dense material so that it can hold the penetration of oxygen underneath the silicon, okay, silicon oxide here, the mask, so that we can reduce the Bursvik by increasing the silicon nitride or decreasing the base oxide. But if we try to decrease the Bursvik, then because of the stress due to the volume change, the dislocations and crystallographic defects, okay, dislocations can be formed at this Bursvik area, okay, that the crystallographic defect is going to be propagated from here, okay. So that is, we cannot actually decrease the base oxide to too small, too thin, or we cannot increase the silicon nitride too thick to decrease the Bursvik. So some part we have to live with the certain length of a Bursvik. These days, the Bursvik length is typically 0.7 microns at each. So you build the transistor here, and at each, it's 0.7 micron is going to be wasted. And after that, you are going to have a field oxide, which is really working to block the communication between the transistors. Okay, that's what that is. Of course, in the bird's head, even though the fully recessed process, we have a bird's head, and we have a planarized surface, reasonable planarized surface. But this bird's head is also can create a defects along this direction, things like that, and then the bird's head area is just a waste, just like the bird's beak. So, and the process is a little bit complicated than the normal semi-recessed process. So nobody, as far as I know, nobody is doing the fully recessed process in the industries. Okay, now let's just take a moment to see the equipments that we are going to use for the oxidation process. Okay, all the properties of insulated silicon oxide and silicon nitride and things has been tabulated in this table, so you just can use this as a reference. Well, this is the typical example of oxidation furnace. It doesn't have anything. It just have a loading system and then open furnace. And there are three different kinds of oxidations. One is a dry oxidation, which is on the top of this figure. Now, dry oxidation is nothing but you just put the oxygen on the silicon wafer at elevated temperature so that the silicon plus O2 and the silicon oxide, that the chemical reaction happens on the surface. That's the simplest one. And here the N2 is carrier gas. Okay, you are going to flow some of the oxygen, and then you have to carry this oxygen into the furnace by this N2 gas. Okay, and this is the wet oxidation equipment. Here, what you do is not only using the oxygen, but also there's water, H2O. Water is going to be flowed into the furnace. And later we are going to discuss about this, but the wet oxidation has a higher growth rate of the oxide than the dry oxidation. Very fast. It's a very high oxidation rate comparing to the dry oxidation. So this is a very serious, important equipment. Okay. And lastly, we have a pyrogenic oxidation. And in this pyrogenic, we use the oxygen gas and the hydrogen gas separately. And with the carrier gas, you flow those two gases into the furnace so that at the silicon surface, now hydrogen and oxygen is going to react to form water. And it end up with the wet oxidation anyway. But this pyrogenic oxidation has to be distinguished from the wet oxidation because the oxidation rate and oxide quality is different. Okay. So after this equipment review, we have to go for the growth kinetics of the silicon oxide. What time is it? Okay. For the growth kinetics of silicon oxide, we are going to use the Deal and Groove model. Okay, this is a very famous model, which has been developed in 1940s, I guess. Okay, and basically what it does is that when you look at the silicon oxidation process, you can distinguish three regions. Of course, the silicon surface, and in the middle of the oxidation, you have some silicon oxide on top. And then at the surface of the silicon oxide, you're going to have gas ambient, which contains the oxidant. Okay? So we can have these three regions, and basically what we are going to talk about is we are going to have three fluxes here. One is from the air come to the silicon oxide across these boundaries, okay? And the other flux is the oxidant flux, which is moving from this surface to the surface of the silicon, okay? And then at the silicon surface, the oxidant which arrives at the surface has to be consumed. So we have three fluxes. One is F1 from the gas to the silicon oxide surface, and F2, which is a diffusion process, actually, of a silicon of oxidant from across this silicon oxide, And finally, we have a flux, which is related to the surface reaction. The chemical reaction actually happens at this surface. Silicon plus O2 to silicon oxide, that really happens at the surface. So F1 is kind of a gas and atomic absorption related thing, and F2 is just a diffusion related thing, and F3 is a chemical reaction related thing. Okay? And for each flux, the first F1 is related to the mass transfer coefficient. Okay? You just set the mass transfer coefficient, you just set there is a concentration gradient. That concentration Cg is the oxidant concentration in the gas, and Cs the oxidant concentration at the surface. So we are talking about this dotted line here. Okay, this concentration gradient is related to the flux by this coefficient. Whenever you come to the words coefficient, it means that we don't know anything about it. Okay, we just put some constant, which should be, well, because the concentration gradient should be related to the flux somehow. So we just empirically set this equation, and then we say this F is a coefficient, mass transfer coefficient, things like that. Okay, and oxidant concentration in a gas, we know that, but oxidant concentration at the surface can be related to the pressure, partial pressure of oxygen, partial pressure of oxidant, precisely speaking, with this Henry's law. Okay, Henry's constant is going to relate to that. And we set the C star, and C star is here. You know, C star and C naught has been depicted in this diagram. C star is the equilibrium concentration of oxidant in oxide, which would be in equilibrium with the partial pressure of oxidant. Okay, so that this C star equilibrium concentration is related to the Henry's constant, and using the ideal gas law, we can relate it, the F1 with the Henry's law and the C star, things like this. Okay, this is the final thing that we have to use. And F2 is nothing but the fixed first law, concentration gradient and the diffusion coefficient. And concentration gradient, this X naught is the thickness of the oxide, and the C naught and the Ci is the concentration gradient inside the oxide. Okay, that's simple. And F3 is more simple. We use chemical surface reaction constant. Okay, and then that is related to the surface concentration Ci. Okay, so this reaction constant is a thermally activated process, which means we can represent this Ks reaction constants in terms of the Arrhenius plot. Okay, the Boltzmann plot. We are going to get to that in a minute. In a steady state, F1 should be equal to the F2 and F3. Otherwise, the oxidant has to be accumulated or depleted in some regions. Okay? So, in a steady state, we should say that the fluxes should be the same, and the slowest flux will control the other fluxes as well. Okay? And you equate all those things, and then you end up with some equations here, and it has the limiting cases, but if you just the limiting cases has related to the diffusion coefficient of the oxidant inside the silicon oxide. And by putting F1 is equal to F2 is equal to F3 in a steady state, all these fluxes can be represented with this equation, and the oxidation rate actually is nothing but the thickness of oxide with respect to the time. That is the oxidation rate, and that is the flux F divided by number of silicon oxide, number of oxidant molecules per unit volume of oxide. That is the oxidation rate. Okay, that the flux is the number of oxidant molecules passing in a reference plane per second, something. Okay, so the oxidation rate is F divided by N, and we know the F can be represented as equation 8. Then we end up with this. Okay. Here, the number of oxidant molecules is different in a dry oxidation and the wet oxidation. You see, the wet oxidation has more dense silicon oxide than the dry oxidation, dry oxide. Okay, dry oxide, I should. Okay, so you are going to have this second order equations with the two constants with above equations, and that one constant is A here in this equation, and another constant is B, but instead of A, the B over A is a special constant because it is a linear rate constant. We call that the linear rate constant, and that is more often used in the experiments. So, what the conclusion of this deal and groove model is that we end up with this equation with this constant, and this equation has two limiting cases. We can analyze this deal and groove model in the two limiting cases where the short time means at the beginning of the oxidation, and the long time means at the end of oxidation. Okay, after some oxidation process progresses, that is the long times. So at the beginning, the oxide thickness is linearly related to the time. So this equation says, at the beginning of oxidation, if this is the oxide thickness and this is the time, at the beginning we are going to have a straight line here, and the slope is B over A, right? And after some oxidation progresses, then we're going to have the parabolic relations, which is something like this. And that oxide thickness is proportional to a time like this. Okay? And then, for this parabolic reactions, the rate constant is going to be called B, and this linear region, the rate constant is going to be B over A. So in next week on Tuesday or no Monday, we're going to discuss about this b over 8, the linear rate constant, and b, the parabolic rate constant, more in detail. Okay, and then we analyze some of the experimental results that we can obtain, which support actually the Dylan Grove model. Okay, so I'll see you on Monday next week.